Welcome to my new calculus channel. My name is John Gabriel. Today, I'd like to talk about a few of the misconceptions of mainstream academics and to show you how flawed their thinking is in many ways by revealing, once again, a different perspective on the same ill-formed concepts that you'll find in mainstream calculus, which is flawed, and also in the thinking of modern academics, which is terribly flawed also. So let's begin. Right, now, if you'll recall, some time ago, I was discussing algebra. In fact, in one of the lectures that I gave on my ebook, I was talking about where the notions that we have in algebra come from. So algebra was realized directly from geometry. Okay, it wouldn't be known today had the ancient Greeks not realized geometry. No mathematics whatsoever would have been realized. So geometry is really the foundation of all mathematics. Now, the Arabs, who are normally credited with algebra, didn't just sit down one day and decide there were concepts such as equations, variables, and arithmetic operations. All of these concepts are meaningless without geometry, from which they are directly derived. Now, an object, not a set, by the way, because a set is an ill-formed concept, is the idea of being, and its first property is stated very cogently. Objects that are equal to or the same as a given object are equal to one another. That is the first common notion in Book 1 of the Elements, okay? So it applies to anything and everything, whether it's a tangible or intangible object. It can be a magnitude, a ratio, a number, an equation, a variable, an orange, a sauce, an animal, anything, okay? But an object cannot both be and not be. This particular peculiar property and strange property belongs only to the ill-formed concept of set, okay? For example, you can have a set which is an empty set, which is complete rot. Now, the idea of equation is realized directly from notions 2 and 3. And I've summarized those two notions, but you can read them in the Elements. Objects that are changed or altered in the same way are equal to one another. Those are notions 2 and 3. Notion 2 says basically that if objects are subtracted, if the same object is subtracted from two equal objects, then the result is the same. Likewise, if an addition is performed, the result is the same. Change, in the case of magnitudes, means arithmetic. Now remember, a magnitude is not a number, okay? A magnitude is just the idea of length, right? Or distance, or size, or dimension, okay? Or mass, or volume. It's not a number. A number describes the measure of a magnitude, okay? I was the first to correctly state the definition of number in all of human history. Euclid tried to do that correctly, but he failed. I succeeded. And the only reason I succeeded is that Euclid actually knew exactly what he was doing, and so did the ancient Greeks. But of course, if you're a pioneer and you're writing down things for the first time, you don't always write it down perfectly. So now, in Proposition 12 of Book 5, all the binary operations of arithmetic are defined with magnitudes, okay? So what is the difference between a magnitude and a number? Well, you know, let's just go over here. I want to draw on the screen, so give me a second. Okay, so now, you'll see that mainstream academics will often, let me just get a pen here. Make it black. Okay. Now, mainstream academics will often draw a particular interval like this. Okay. Let's say 0 and 1. And they'll call this a set. But what is it a set of? Exactly what is it a set of? A set by, actually, there is no formal definition of a set, but let's look at, lay set theory, where a set is basically comprised of distinct elements. Now, what are we talking about if we're talking about distinct elements in this particular interval? Are we talking about numbers or magnitudes? What are we talking about? Now, is every possible magnitude in this interval, is every magnitude in this interval possible? Well, we'd need to have that if we were talking about continuity, right? And so, yes, every magnitude is possible in this interval, but not every magnitude in this interval has a name. Okay, how do we arrive at a name? Think about it for a second. How do we arrive at a name? Through measure. Okay, we measure a particular distance and we give it a name. For example, this distance here is given the name 1, okay, because we've defined it to be the unit. Okay, we chose it to be the unit. We can choose any distance to be the unit. Half of it also has a name. It's a half, right? Okay, so obviously we cannot provide all the measures of the magnitudes in this interval. Okay, we cannot measure all of them. Therefore, there is no set described by this interval. What is it a set of? Is it a set of numbers? Well, numbers are the names given to all the distances, but we don't have those names, and there is no such thing as an infinite set. As you know, infinity is a bogus and a junk concept that does not belong in mathematics or any other field of rational thought. Okay? So now all the arithmetic operations are defined in proposition 12. Okay? Every single one of them. And how are they done? They're done with magnitudes. You may recall at some or other time, and let me just close this, that I showed you this particular applet. Now, we don't have to have labels here for these magnitudes, okay? Let's just get rid of the labels, like so. And it doesn't matter how we move these, because this particular light blue line divided by this line here will always be equal to the ratio of the red line and this will always be equal to the ratio of the red line and this light blue line. So this dark blue line divided by this line, this dark blue line divided by this line, or actually divided by the black line, the dark blue line divided by the black line is equal to the red line divided by the light blue line, okay? So this here gives us or shows us how division and multiplication takes place purely with magnitudes. We don't even need to know what these are. We could have written the color, just the color here, okay, and said that these are possible. And why? Because these two triangles here are similar, all right? So let me get rid of that. Now, so I showed you that in several videos in the past. You don't need numbers to do arithmetic, okay? All you need are magnitudes. And that's what I was showing you with a particular interval there, 0, 1. You can't really call it a set because a set consists of distinct elements. What distinct elements are you talking about? Are you talking about magnitudes or numbers? Well, first of all, if you're talking about numbers, you don't have all of them. And if you're talking about magnitudes, you don't know what they all are, except that if you choose a particular magnitude in there, you know that it has to be possible, right? In algebra, in arithmetic, in any operation of arithmetic, you know that that magnitude which must be possible, which also negates the need for real numbers in the mean value property. We don't really need to know anything about the real numbers being complete or anything like that when we use the mean value theorem. That's just ignorance on the part of mainstream academics, and I have proved it to you because I was the first to prove the mean value theorem constructively. So this proposition is that which makes all algebra possible, right? Now, over the past 2,000 years, people in math academia have not understood these things. When we write P over Q, yes, we don't mean P divided by Q. We mean the number that is represented by that ratio, okay? And I've shown that to you. If you look at my past videos, you'll see exactly what it means. There's no division pending there. Nothing has to happen so that, you know, P over Q is defined. It's defined perfectly as it is. We don't do anything else. There's nothing that is pending or left over. Now, in the same way, dy dx is a well-formed number, meaning dx can never be 0. Okay, and I've also described this in very fine detail in past videos, so I'm not going to spend more time on it. Now, I want to show you some of the stupidity of mainstream academics. Okay, now, in the past, you'll notice that I've often referred to this particular ratio here, sine x over x. Now, I want to once again go back into draw mode on the screen. So I'm going to press here, screen. All right, so now you'll see over here this particular ratio. Now, let's just get a darker pen. Okay, all right. So this particular ratio here, and I don't know why it's not the same color all the time, but anyway, that's not important. This here is not in its reduced form, because in its reduced form, it's going to look something like this, okay? It's going to look something like this. Let me just get a dark pen so you can see what's happening here. Okay, it's going to look something like this. 1 minus x squared over 6 plus x over 4 over 5 factorial, and so on, right? Okay, that's what it looks like in its reduced form, okay? Now, and this particular function is very well defined at 0, okay? It's actually equal to 1. There is no hole there, because if you put 0 in all these x's, then we have 1, right? Now, idiot mainstream academics will tell you it's not defined at 0. Actually, it is defined at 0, because it's the only reason you're not able to get it in this form is that it's not in its reduced format, okay? And the reduced format is this. If we multiply this whole thing here by x over x, and by the way, we can't multiply it by x over x if x is 0, right? So x, it's not even a question about x being 0. We don't even, this is always 1, regardless of what is x. And naturally, x cannot be 0, because 0 over 0 is meaningless crap, okay? And if we multiply that, then we get sine x over x, right? Which supposedly isn't defined at 0. That's obvious nonsense, right? And you'll notice that if you take more terms of this here, you start getting more parts of this particular curve, right? So, and you might say, well, this is a limit. No, it's not a limit, because if this is a limit, then sine x is not defined at 0, okay? Because you'd have to put 0 in all the x's in this format, right? You'd have to put 0 in all the x's in this series format of sine x, all right? Now, this here doesn't really give you sine x. It only gives you a rational number approximation. And the only case that you can get an exact value here is that everything falls away if you put a 0 in x. In other words, this whole thing actually evaluates to 0 at 0. In the same way, this whole thing here evaluates to 1 when you put a 0 in there, right? And g of x is equal to sine x over x. So this here being equal to g of x is evaluated at x is equal to 0, right? And there's another similar problem to this, again, that idiot mainstream academics also miss? Let's go to it. It's given in this particular example. So now, this example here states that e, the number e, or e, the function e to the x, this function here, can be defined in terms of a binomial, as you see over here, right? So it's actually, if you study this, and I've given it to you in previous videos, you'll see that e to the x is equal to f of x of 0. Similarly, if we want to get e to the 0, it would equal to f 0, 0. Now, if we put f 0, 0 here, we actually have, let me write on here now again. Let's do this again. If we put inside here, in this definition here, if we put f of 0, 0, which is equal to e to the 0, which is equal to 1, right? It's the same as us writing 1 plus 0 times n to the 1 over 0, right? But can you evaluate it in this form? Of course you can't, okay? There's no way you can evaluate it in this form. Think about it. This here is meaningless rot. But of course, if you expand it, as I have here, and I've shown you here, you can actually see that all these will fall away because both the x's and the n's are 0. And that's how you get 1. Okay, so there is no limit there. It's actually very well defined when x is equal to 0. Similarly, we can find a value for e to the 1, right? And there's another function that you could use to do that. And I think it goes something like this. It goes something like 1 over x, I think it's 1 over nx to the n. Okay, I think it's something like that. But I've also provided that particular solution. I've also provided that in another article and also in several other videos, which you can find on my shared drives online and in the web. Okay? Now, you'll see here that again, as we add more terms, and this is how we add more terms here. If we come along here and we push this n here, this blue curve will become more like this one. All right? Don't believe me? Let me show you. All right? See here, look. See that blue curve? It's starting to become more and more like that one, isn't it? Okay, and the same thing happens also in the previous one, right? This one here that I showed you. So for example, if we wanted that particular function, and let's do this. If we added another term, we'd see this red curve here come closer to this side, right? So we could say, let's add the next term. Let's add the next term, and that will be 18 and 19, right? And you see that? So we've got more now. And if we continue that way, this red curve will follow the dotted path, right? Which is this particular function here, which is g of x, right? That's right, which is g of x. So, I think that's basically it. That's what I wanted to show you here with these two examples, but there are many more like this. And modern academics are incredibly stupid. Ignorant, stupid, incompetent, arrogant, vile, jealous, and evil. All those horrible qualities, they have them, and they possess them. So nobody has come forth and ever stated, you know what, John Gabriel is right, and we need to change what we're doing. Well, actually, some people have come forward. Not telling the truth there. Quite a few people have come forward, and more are starting to see the light, which is encouraging to me. Both professors of mathematics and students, so I shouldn't be that harsh. But you'll see a lot of libel about me on the internet. And if you believe it, you're obviously a moron. Now, going back to my presentation, so I think I've shown you in this little video just a few examples of ill-formed concepts and how ignorant my intellectual inferiors of the past 2,000 years have been. And when I refer to intellectual inferiors, I mean all of you, basically, because nobody was able to formulate a rigorous calculus like I did, and to reveal all these facts and enlighten you as I am doing in all these videos and articles that I've written. Now, you can find the most important book that was ever written by me, by the way, here on the internet, and it's free. You don't have to pay a single cent for it. Just click on this link and you can download it. It consists of roughly 123 pages with about 13 chapters, I think. It is the most important book ever written in mathematics. There is no other book that has the amount of facts and knowledge, well-formed facts and concepts that you find in this book yet. This here contains what Euclid attempted to do, what Newton, what Leibniz, what Archimedes, and everybody else failed to do. Okay, and this shows you the first formulation of calculus, the first rigorous formulation of calculus. Well, I think that's pretty much it. I'm a little out of breath right now. And what I'd like you to do is don't believe anything I say. Download the book, read it. You don't have to pay anything for it. It's free. And find out what is the meaning of mathematics, where numbers came from. Read my articles online. Visit me on LinkedIn. I've written several articles on LinkedIn too, but the majority of my articles are on my shared Google Drive. And obviously, you want to go to my website here and read this link, because there are many links to articles and videos and lots of very juicy information, which you won't find everywhere else. You will see none of this information on any other site or on any other book. It has never been published. Okay, I am the great John Gabriel, the discoverer of the first and only rigorous formulation of calculus in human history. I hope you enjoyed this little presentation. This is a new calculus channel. Till next time, goodbye.